Uh, Good evening, everyone. Am I audible to all of you?
Yes.
Yes.
Great.
Hey, Ali. Just FYI, my whole class gonna attend to this lecture. I have I think 77 students in the class. Hopefully, all of them gonna attend. So you got a big audience today. So.
Oh, that's wonderful.
Mhm.
Great. Thank you for your support.
Thanks. Okay, so let me start. So good evening, everyone. First of all, thank you all for taking the time to be here today. We are thrilled to have you join us for this special occasion. It's a big day for us as the CR2C2 Student Leadership Council is officially launching its first event. So we warmly welcome you all to the Leadership Training Workshop. So let me introduce myself. I am Komal Gulati, co-chair of the Student Leadership Council, and with me is Oladimeji Alaka. So he's the chair of the SLC. So Basit, would you like to say hi?
Hello everyone.
So before we begin, I would love for all our SLC leaders who are here to unmute and say hi. So we truly appreciate your support in making this event happen. How, Suhela, Tamina, everyone, if you could just say a hi. Are you all here?
Yes.
I think so.
Hi, I'm Hao. I'm from University of Georgia. And thanks so much for Dr. Green for support of our Seattle City Students Leadership Council. Thank you.
Yes, and I want to especially thank Hao and Dr. Yang for helping us to invite Dr. Guin. So we really welcome you. And now I would like Dr. Karimotni and Dr. Richardson to say a few words before we begin our session.
So good evening, everybody. Thank you so much, Kamal. This is great to see that the idea of Student Leadership Council is growing in such a great way. And today is, by the way, we are in the engineering week. A lot of the students are, and a lot of the audience today are engineers, but I'm expecting that maybe there are also people outside the engineering discipline as well. That's great. And part of this workshop series was intended to provide even some additional skills that we engineering students may not have on whether on management sides or on some other leadership skills or even a little bit more knowledge on data science that we might be needing. And this is great idea from our Student Leadership Council. Thank you, the entire leadership team, as well as the speaker today, Dr. Guin. Thank you so much for accepting and supporting this event, and everybody who supported. A lot of effort I have been witnessing our Student Leadership Council, and thank you, Dr. Richardson, as well, to help our student leadership as well. But a lot of effort has gone through it, and hopefully everybody is going to be enjoying today and the rest of events tomorrow all the way to Friday. The weather is not good, and we might have some of the events to be fully online. But it's a good thing at the same time that still we can have online. We have learned how to be robust to switch immediately to a sort of online mode as needed. Thank you so much, and look forward to this series of workshops.
Thank you, Dr. Karimotni. We'd also like to hear a few words from Dr. Richardson.
Good evening, everyone. It's wonderful to be here. For those of you who don't know me, my name is Sydney Richardson, Associate Professor of Leadership Studies. So outside of engineering, but excited to work with SLC and the rest of this group to just learn more about this and offer opportunities to other people, other students from various disciplines as well as engineering. So I'm very proud of SLC and everything that they are pulling off. And so I echo the words of everyone else, and I hope you enjoyed it this evening along with the rest of the workshops.
Thank you so much. Now, I would also like Basit to say a few words about what we are, what we do. So yeah.
So hello everyone. So my name is Basit. I'm the student chair of the student CR2C2 Student Leadership Council. And then our aim is to actually find a way of bringing students together, teaching them things regarding leadership, and also like bringing events like this to bring our students together, and also like to equip them with some of the knowledge they need to like thrive in the world out there. So, and I also want to like use this opportunity to acknowledge the incredible efforts of some of those who actually help with these events, including Komal. He actually put in a lot of effort. How Sohilia, Javier, Amina. I really, really appreciate your effort. And also, I want to use the moment to also like thanks the CR2C2 team, Dr. Hali, Dr. McBride, and Dr. Richardson. Your effort is really, really valuable, and we are really glad that you also like give us enough time to be able to like pull this off. Your dedication has been instrumental in bringing these events to life, and I deeply appreciate your commitment to the SLC and the CR2C2 mission. It is true teamwork and shared passion that we continue to create opportunities for growth, learning, and leadership for students in our community. Thank you once again, and thank you everyone for your support.
Thank you so much, Basit. Now it's my pleasure to introduce our speaker for today, Dr. Angshuman Guin. He is a principal research engineer in the School of Civil and Environmental Engineering at the Georgia Institute of Technology. He returned to his alma mater as a faculty member in 2007 after gaining industry experience. Dr. Gwyn's research is centered around a fundamental question: how do we enable and empower system managers, researchers, and users to make effective data-driven decisions? His work focuses on developing innovative methods for data collection, quality assurance, and processing, transforming raw data into meaningful insights across various timescales, from real-time analytics to long-term forecasting. Currently, his research covers areas such as freeway operations, connected and autonomous vehicles, intelligent transportation systems, transportation safety, traffic simulation, and data management. Dr. Guin has presented at numerous international conferences, and his research has been published in renowned peer-reviewed journals. He actively contributes to the Transportation Research Board, serving on committees related to information system and technology, and human factors in infrastructure design and operations. Beyond academia, Dr. Quinn is passionate about translating research into real-world applications. He is also the co-founder of Insta Data Systems, a company focused on data analytics. So without further ado, let's begin our session. Dr. Quinn, the floor is all yours.
Thank you. Let me see if my screen, if you're seeing my screen.
Yes.
Okay. All right. So I wasn't quite sure of what you all are looking for, so I am just going to go ahead and present some data analytics for decision support with some real world examples, and hopefully it'll be interesting. So if I can get this moving. All right. So to ensure that we are all on the same page, let's go over some definitions. By traffic operations, we refer to the day-to-day management and control of traffic flow on roadways. There are several tools that are used for this, depending on the type of roadway. For interrupted flow traffic, we use different strategies such as stop signs, yield signs, roundabouts, and of course, traffic signals. For uninterrupted flow, such as on freeways, traffic operations takes the form of incident management, ramp metering, variable speed limits, etc. So the goal of traffic operations is typically a dual mandate of improving mobility and improving safety. So I understand this is a lot of the audiences is the transportation engineering class students. So most of you probably have an idea of this, but I'm just going to go over some of these ideas at a very high level so that we have everybody on board. Okay. So data analytics is the process of translating data into meaningful insights. Simple as that. We'll go into more depth, so I don't want to go into that right now. Decision support systems provide the ability to leverage data and analytics to provide information and insights to the decision makers, or directly in a feedback loop into real-time operations control systems. And so typically these systems have aligned with the concept of intelligent transportation systems, a word that 10 years ago used to be much more used than what they are now, than it is today. Means nowadays you hear all about connected vehicles and automated vehicles. Those are the buzzwords. But anyway, so intelligent transportation systems broadly encompass the use of advanced technologies to improve transportation system efficiency and safety. So you can think of decision support systems as the middle stack. So ITS uses ITS, or intelligent transportation systems, which we call ITS. Means it uses sensors to collect the data. The decision support system analyzes the data, either completely automated or with a human in the loop in the middle, and comes up with these action items. And the ITS control systems then enable the implementation of these action items in the transportation network. Okay. So moving on. So I'd like to take a step back and look at the evolution of traffic signals to understand the role of data in traffic operations. It's just an example of traffic operations. Means that's one side of traffic operations is traffic signals. It's on the interrupted flow traffic. There's a whole another side on the freeway side, but we are going to walk through this as an example. So that in the 1800s is your traffic signal, right? A person directing traffic. So it was around 1868 that the first traffic signal was implemented with a gas light at the top. There was some unfortunate event with a fuel leak, and the person standing under that died. Anyway, that put a break in the works, but it eventually came back. And it was around 1914 or so when we saw things starting to get automated. Right? Instead of a traffic police making a decision, the signals were now run on a fixed cycle time. And while the advent of the automation in the traffic signal controller provided relief to the traffic police workforce, it was not until about 1928 that we first used data to drive the signals. At this point, once they came up with a system where a mic was used as an audio detector. So drivers were required to honk their horns when they pulled up to the stop bar, which was detected by this acoustic sensor and was used to chase the signal. So that was the first implementation of data in the loop to drive the control system. Around the 1950s, there were some additional automation. Now the vehicles, when the vehicles pulled up to the signal, a pressure plate was used to detect the presence of the vehicle, and that placed a call on the signal controller to get a green signal. The 1960s saw the advent of the induction loop detectors to detect the presence of vehicles, and these were used for driving the traffic signal controllers. In fact, these sensors have been so reliable and affordable that we still use them 6 decades later. In the 1980s, we started seeing more advanced signal control systems, such as the coordinated systems, where you create the green waves, as you can see in this the small graphic at the bottom, where you try to move the traffic without stopping at any of the red lights. Yeah, but it's important to note that while the logic for the coordinated signal control is more complex than the isolated signal control, This helps us achieve better efficiency, but we might not be still leveraging the power of data analytics for this, except maybe historical analysis of the data, but not in a real-time fashion. Well, you could use it, but you could get this done even without using it. So the data is used more for occasionally optimizing the signal timings. Around the 1940s, we had our first freeway in the US. But after the Federal Highway Act of 1956, we started seeing more widespread use of freeways. And it was then around the 1990s that we started seeing the advent of these transportation management centers, where we saw much more centralized control of traffic operations. And the traffic operations coagulated around these transportation management centers. This picture, however, is not from the 1990s, and it's not with those LCD screens there. Anyway, the primary justification of a lot of these traffic management centers were centered around in incident management, especially those dedicated to freeway operations. Right. So the process for the incident management was still pretty much manual. The operators the operators on this floor, they were still using CCTV cameras to keep an eye on the freeways and find out incidents, and they're receiving calls from the motorists to know about where the crashes were occurring and responding to those. Slightly later, or around the same time, we saw the advent of the incident detection algorithms, which now started leveraging the data. So yeah, one class of incident detection algorithms were looking at the vehicle speed and count data to identify anomalies that would indicate that an incident has occurred. The other class looked at processing video streams to identify stalled vehicles. Okay. Around this time, also we saw the advent of electronic toll collection technologies. However, it probably took another decade or so before we saw a real-time looping in of the data to drive dynamic pricing. In the 2000s, we started seeing the concept of integrated corridor management starting to take shape with freeway management, arterial management, incident management, transit operations, all being less siloed. They started working together with collaborative management. The glue here that enabled the communication between the systems was, of course, the data generated by the sensors in each of these systems. Of course, it goes without saying that the latest in this area of operations, if you can block out the noise on the autonomous vehicle news for a moment, is the technology for the connected vehicles. Connected vehicles come with a lot of advantages that can be gained from this implementation. The low latency communication between the vehicles and the infrastructure has the potential for benefits in terms of safety, mobility, commercial vehicle operations, traffic advisories and warnings, and so on, if we can come up with an agreement on the standards and the radio bandwidth usage. So anyway, I won't go into that. So now, wish I could see my clock. Okay, we're doing okay on time, I hope. So I'll go into let's look at what traffic operations look like close to home. So let's look at some examples of ITS technologies being used in traffic operations in Georgia to get some context of how where are the opportunities for leveraging data to develop and use the decision support systems. So Georgia has one of the has one transportation management center in Atlanta and several smaller traffic control centers spread across the state. The backbone for the traffic operations in the Metro Atlanta region is the fiber backhaul network that was initially established just before the 1996 Olympics and has been expanded over the years to about 307 center line miles. So this provides a high-speed conduit over which the data can move back and forth between the compute locations and the detector locations. Right. In addition to the TMC, there are the Transportation Management Center, which is called TMC. In addition to the TMC, there are 25 or so more hub buildings that also house the compute equipment closer to the field device location. So it provides a distributed network. That architecture, the ITS architecture has changed a little bit, where we have eventually moved more of the compute to the edges. So instead of all the raw data coming back to the hub buildings or the center, with more of the decisions, the real-time decisions have been pushed out to compute blades residing on the inside the cabinets at the bottom of the poles for the detectors. So a typical installation site looks like this. The fiber drop from the trunk line goes into an underground pull box. From there, it connects to a field switch, which resides in a traffic cabinet. The CCTV camera with a pan-tilt zoom capabilities is on a pole right next to this cabinet, which provides the capability for monitoring the traffic conditions. In addition to that, there are one or more fixed cameras which serve as the video detection system viewers. So the video from these fixed cameras are streamed back to either one of the hub buildings or to the bottom of the pole to that cabinet, where it's processed to generate the vehicle counts and speeds on a per lane basis at that site. Right. This is an example setup of the cameras on the freeway. You have a dome camera at a lower height, where which is the pan-tilt zoom camera. You have the a concurrent fixed camera on the top of the pole. There's about say the green dots on the map on the bottom left, that those are the locations for those monitoring cameras there. And this view there here means if you have been on the 511 Georgia 511 website, you can see all of these, as it has the streaming videos from these pan-tilt zoom cameras that anyone can look up. So we have about 5,000 plus detection stations. So a detection station is the stations are probably about 1,000 or so, but each of these lanes is a separate is coded as a separate detector. So that's where that 5,000 number comes from. One of the major responsibilities of the traffic operations department is incident management, and clearing incidents rapidly and in a safe manner is probably the operation that has the highest impact on congestion mitigation on the freeways. As the Metro Atlanta area is managed by the highway emergency response operators, or the HEROs. The CHAMP operation is what provides much more widespread coverage, but their service is also spread much thinner than the hero operators. This shows an example of a video detection system being used at an intersection. So that's another example of ITS being used on the interrupted flow streets. This is slightly dated, means that this is the SIGOPS regional map where it shows how the entire region is divided into operation zones, where Georgia has one of the best operations for traffic signal optimization and control. Thanks to these programs that have evolved over time, as the RTOP program, now the SIGOPS program, and so on. Another example that's probably not that popular is the variable speed limits, where the speed limits on the freeways are changed in real time in order to provide a way to control the traffic on the freeways to reduce the impact of vehicles heading into the back of a queue and so on. On the transit side, we have the GTFS RT streams, which are being generated by the vehicles. So GTFS is general transit feed. So standard, I guess, in real time. So it's essentially automatic vehicle location data for the buses, so you know where every bus is at any point of time, which can drive the screens like this you see on the right, where you get the arrival times of each bus in real time. You also have data coming out of the transit buses in terms of automatic passenger counts, of course the GTFS, adherence tracking data, where you can see whether the buses are running late or on time, what percentage of the time they're running on time versus late. And these can drive transit signal priority, which I'll talk about more later if we find time for that. Coming back to the freeways, we have a whole system of changeable message signs, which used to be much more useful and popular several years ago, until Waze and Google Maps kind of have taken over the responsibility of transmitting information to the users. When people get much more of a heads up using Waze than probably looking at the changeable message signs. However, this is still the official way for the transportation management agencies or the operations folks to transfer information directly to the public. Other technologies in use in the Atlanta area, the Metro Atlanta area, are the HOT lanes or the express lanes with variable pricing and dynamic tolling. We have both buffer separated operations and barrier separated operations. When on the I-85 corridor, means we have buffer separated. Means in the newer facilities we have barrier separated, whether the traffic is completely separate. We have reversible lanes, where we're using to add capacity, directional capacity during the morning peak and the PM peak. So with those examples now in our rear view mirror, means I think we can now look at how once we can use analytics to enhance traffic operations in real time, or for planning of traffic operations. So data analytics has four primary types or layers, with of progressive complexity, right? The simplest layer is descriptive analytics. Descriptive analytics tells you what happened in the past. You aggregate data, plot out the data, etc., to see the patterns in the data. Right? The next layer is the diagnostic layer. And diagnostic analytics helps you understand why something happened. So the patterns you are seeing in your descriptive statistics, why is that happening? Right? You use the patterns in the data to draw correlations or, if feasible, causation models using that data. The next layer is the predictive layer. So once you have figured out the correlations, you try to predict that given the emergence of certain patterns, you try to predict what would be the most likely future scenario. And the most advanced layer is prescriptive. In prescriptive analytics, you get recommended actions for you to take that could affect the outcome. So this helps us when we get to the prescriptive analytics, we get to create full automation, where the data automatically produces the recommendations that generates the action items that help us obtain the desired effects of reduced congestion, improved safety, and so on. So let's walk through a real world example of a decision support system that we built for GDOT. I think that will give us an idea of what's involved without talking in abstract hypotheticals. So for data analytics, your starting point is obviously the data, right? The base data set that gives us the highest resolution and the most current field conditions for our GDOT implementation was the GDOT ITS data, which consisted of the vehicle speeds and counts generated by the video detection system. Now, to enhance this information and the inferences we can draw from this data, we fuse this data with other data sets, such as the incident data. Right? So, means a significant portion of the congestion, or some part of the congestion, is explained by recurring bottlenecks. A significant part of the congestion is explained by non-recurrent congestion, which comes from incidents. So to understand the complete picture of what is going on in the travel behavior, you need both the recurrent congestion information as well as the incident information to complete the picture. Right? Also have the NPM RDS data. So the ITS data is mostly concentrated in the Metro Atlanta region, where we have direct visibility from the video detection systems. For statewide visibility, we have the national NPM RDS data set, which covers the entire national highway system. We also have data from external data providers such as HERE or INRIX, and so on, who provide more pro-vehicle based data. So there you don't have the count data, you have speed and travel times. Have Waze data, where Waze provides both incident information and some form of speed or travel times. We have data from SRTA, the State Road and Tollway Authority, from where we can get all the toll tag information, the dynamic pricing information, and so on. Weather impacts the traffic behavior, the driver behavior. So whether it was raining on a particular day could explain the increased congestion. So instead of trying to attribute our congestion or the deviation of congestion on a particular day to some other factors, we need to check it against the weather. So that fusing that information is of value. Then we have data from our transit authorities, data from the signal operations on the interrupted flow roads on arterials. So now that you know your data set, how do you go about building your analytics platform? The first step in this process is accepting the fact that real world data is non-ideal. It has noise, some random, some with inherent upward or downward biases. It also has gaps or outages when equipment fails or communication fails. So once you accepted that, you start building the filtering and deduplication process that ensure consistency in the data. So in the data science world, you'll probably hear the term ETL thrown away a lot, extract, transform, load. So once the data is clean, you load the data up into a system that makes the data readily available. Now, this can take the form of loading the data in some distributed database, or in some specific use cases, the strategy might be to summarize the data to preserve only the relevant information and discard the raw data, simply because the data rapidly becomes stale. Right? As for us researchers, this is kind of sacrilege, means we never throw away data, but for operations, sometimes it does make sense. For example, a good example of this would be BSM data, the basic safety message data generated by connected vehicle technology. So BSM data is generated at the rate of 10 hertz, where a vehicle broadcasts its location. So this data is extremely useful for collision avoidance and other safety applications for about 0.5 seconds. After that individual data point becomes stale and irrelevant for pretty much anyone except a transportation researcher. However, for traffic operations, what is relevant is a high-level abstraction of the data in the form of a derived variable such as a queue length or the congestion level in the data. So for the vast majority of the other use cases, you back up the clean raw data, aggregate it to a summary level, perform some pre-processing computations, and load it up in a semi-summarized data format in a database for use immediately or in the near future. Right? So once you with your pre-processing, you have your key performance indexes or the KPIs, basically the performance variables calculated. You can then build your visualization interface to make it easier for an user to observe and understand the patterns. These steps get you through the first steps of the analytics, the descriptive analytics, where you get to visualization. Now, once you have the pre-aggregated data or the pre-aggregated cubes of data, where you can think of each facet of a cube as a feature of the data set, like your speed is one edge of a cube, your flow is another edge, means your time is on another scale, the distance is on another edge. So say cube, but it's multi-dimensional. Anyway, so you can use these cubes to perform the diagnostic analysis. The analytics platform essentially improves access to the information from this data. You create a consistent data store that is easy to share across agencies. Everyone is looking at the data. Everyone that is looking at the data does not have to necessarily understand the nuances of the cleaning and filtering and the difference between the use of time mean speed versus space mean speed in the computation, for example. Anyway, so you create visualizations that will enable drilling down through the data to better understand the relationships, as this takes your analytics to the diagnostic level. So let's walk through some example screenshots of this interface, and I apologize for the small font, since I was trying to get everything into the page. Hopefully, when somebody is looking at this, you have the benefit of a big screen. Anyway, so hopefully these examples will help us see how a decision support system looks like, what are the features it provides, and how it can help in improving mobility and safety for us. So this screen shows a very high-level dashboard of the real-time performance on a 10-mile segment of the roadway. The I-75 southbound from I-285 to SR 138 in the Metro Atlanta region, towards the south of Atlanta, if you are familiar with the layout. So at the top bar, you see the speed, the vehicles per hour, per lane, the travel time, and a dimensionless index, the travel time index, which makes it easy to compare performances across segments. So the chart at the bottom shows the history of the speed and flow values over a day. What you see with the light dotted lines is the prediction of the speed and the flow values based on the history of performance on that segment. So there's your third level, the predictive piece of the analytics. So in this plot, for example, you can see that while the volumes are similar, there is something else going on, which is causing the speeds to be lower than what the projection was. So if you want to dig deeper into what's causing this, you can go to this interface where you run a custom query. You have the option of looking at different performance metrics, such as the travel time metrics, the buffer time index, etc. And you can look for data for specific days of the week at different aggregation levels and so on. So these are very detailed. I'm not going to walk through each of these, just trying to give you a flavor for what the interfaces look like. So this interface lets you use that same data that you used in the previous interface to generate different kinds of charts. Here's an example of a time series plot, which shows the cross comparison between two different segments across two different months to study if one of the segments have had a significant change in travel behavior as compared to another segment, which can serve as the control. This you must be familiar with these kind of charts. Means our old and tried out scatter plot of speed and flow. Here we are comparing two different periods for a detector to see if there has been changes in travel behavior at that location. This is an example of a bubble chart on a map to show the variation of the travel time indexes across this region. So with these examples, you might be wondering, okay, Mr. Guin, I can see a great diagnostic tool, but how about decision support? Right? The decisions are based on these information being presented. So for example, this chart shows you that the southbound segment near I-75 and 675, that big green blob at the bottom, that has one of the worst performances. So if you're trying to identify which congestion mitigation project to prioritize, this visualization is the one which you'll use to tell you which project you should prioritize to potentially get the biggest improvement of mobility in this region. Now, if you want to dig deeper to figure out exactly which part of the segment is creating a bottleneck, you can go into a bottleneck identification report query, where you can choose your threshold which you use. You can choose different KPIs like delay, duration for which a certain threshold, such as the speed, is below a certain level, and so on. You can also look at a visualization of the space-time chart to see how which bottleneck got fired and at what time of the day, which is the one that gets fired first, which one is where you are actually getting a buildup of a queue rather than an initial bottleneck, and so on. This one shows a heat map of the hero vehicle. So this uses the GPS traces of highway emergency vehicle response operators vehicles to identify where they are spending the majority of their time responding to the incidents. So this can help us inform decisions regarding route changes or shift changes for heroes to optimize their operations. To review the performance of a particular of the incident management operations team, or with respect to particular incidents that raised some concerns, or if you felt like there was extended delays due to a particular incident, you could use an interface like this where you have the timeline of an incident visualized. You can see the lane blockages, the arrival and departure of the hero vehicles, and so on. This is an incident log interface. If you're trying to make a decision regarding where to put your ITS maintenance dollars, this interface would be a good place to start. You can query the system to check whether you're getting good data from the system. Good can be defined in terms of simply the availability of data, or a more complex check of the validity of the data. So this shows this chart is generated from the previous query where you are looking at the data for the month of 2011 compared to 2012 for a particular detection station. Is the shift in the free flow speed, the black versus the red, the top bar, that's the shift of the free flow speeds. That's not real. It's just an effect of a recalibration of the station that you can see by going back through the maintenance logs to verify. Anyway, so the next step in the development of these analytics platforms is to make these detectors self-healing. So if errors such as these exist, there should be these should be automatically identified and corrected by using scaling factors or some other means to ensure that the differences that are being observed are actually related to a change in traffic flow behavior or a policy change or a physical change rather than a detector maintenance or recalibration. Right? So we covered descriptive, diagnostic, predictive. Where does our prescriptive come in? That's more or less an area of active research, and try to go through a few examples to give you some idea of or just give you some food for thought on how we can put that last piece in for the prescriptive piece of the puzzle. So one of the work we are working on at Georgia Tech is the digital twins, where we take rough field data from the field, put it in a simulation, generate high fidelity data, and use that to study different strategies before we actually implement it back in the field. So the high risk strategies or the more advanced strategies are tested in a simulation environment by using the exact same parameters as the real world, by using these digital twins, but without the risk of implementing one of these strategies in the real world by going in blind. Another of these efforts is where we are leveraging data to optimize operations is emergency vehicle preemption. So typically the way emergency vehicle preemption has worked is as a vehicle approaches a traffic signal, the traffic signal goes through the required phases that it has to, like if there is a pedestrian on the path, it has to clear that, or if it has to give a transition through yellow and so on, but it gives a green to the emergency vehicle as quickly as possible. However, if there is an existing queue on the road and the emergency vehicle is stuck far behind on the queue, it's already too late to give the green. The vehicle has to wait. The emergency vehicle has to wait or try to bypass the queue by going into the opposite direction of travel if there is no median, of course. So to make this more effective, we are using connected vehicle technologies to get an early.
I don't know if you've been hearing it, but they've been talking this whole time. Oh, well, I've been playing it in the back the whole time.
Sorry.
So
I'm
I
sorry.
didn't hear my attendance for it.
I'm sorry. What was that?
Okay, I think I'm sick right now, but it's okay. I'd rather be sick now than in Japan.
Anthony, could you mute?
I'm just coughing and congestion. It's nothing. Well, actually, today was really bad, and I had some body sores.
Could you mute?
Okay, I'll continue.
Okay.
All right. So that's emergency vehicle preemption, where we are trying to get an early heads up of the arrival of the vehicle and clearing the queue ahead of the vehicle at the intersection or intersections downstream of the intersection where the vehicle is coming. So transit signal priority is another area where we are trying to use not only real-time data, but the historical data to try and come up with ways to leverage to improve transit operations. Is the conventional TSP strategy has been to do a green extension or early green when the bus arrives close to the signal. But in most of these cases, this whole thing is thrown off whenever the bus stops at a bus stop to pick up passengers or drop off passengers. So how do we come up with strategies to optimize the TSP or still provide TSP operations in the face of this kind of uncertainties? And we are working on developing some ML machine learning strategies to address these. Another one that we recently completed was a congestion precursor identification. So the hypothesis here was that it's we cannot predict incidents, right? Those are more or less random events that if somebody is saying that they can predict a crash, and so you have to take that with a grain of salt. But recurrent congestion means there is we believe that there are precursors that we can detect in the traffic that are instabilities in the traffic that give an impending or that give an idea of an impending failure. And so we developed some machine learning techniques to identify these precursors. So things like these, as these can be your real-time feedback loops that you can look at the data in real time and figure out that there is an impending congestion, and you can plug in one of the tools from your toolbox, such as use a variable speed limit or do an upstream ramp metering to slow down the infiltration of additional traffic onto that segment, do some throttling and so on to try and smooth over that instability in the traffic to avoid breaking down the traffic. You cannot avoid it forever, but at least postpone the breaking down of the traffic so that you can push through more traffic. Anyway, so This one is completely somewhat different, where it's an application where we are looking at how do we use real-time operations to address address multimodal commutes. So for users where they need an extra few minutes if they are on a wheelchair, means if they need extra few seconds to cross that intersection, or if they need indoor navigation help, means how do we provide that kind of information in real time and have the traffic signals respond with pedestrian messages broadcasted over to whoever can listen, whoever has connected vehicle technologies, or the signal can respond in real time as the pedestrian walks up to the signal in anticipation that that pedestrian will cross that, so they don't have to wait at the miss the cycle and wait another 3 minutes for the signal to come to them and risk a jaywalking situation. So anyway, so those are kind of the active research that's going on for the prescriptive part of data analytics. That's kind of all I had. I think we are right on time.
Thank you so much.
Sure.
Thank
Questions?
you so much, Dr. Guin. Yeah, any questions? If anyone has any questions, please feel free to unmute and ask, or you may even like put it in the chat box.
Yeah, any question from the class? I know, I basically all the students come from my transportation engineer class, so we haven't covered too much about the signal operation yet. So
Okay.
maybe, that's why, Dr. Guin gave some background up front there. So hopefully you didn't get lost in the middle of the presentation. But if you have any question, feel free to ask here. Yeah. Oh, basically attendance sheet. I think we keep track of all attendant here, right? How?
Kumo, do we have recording of this, or do we have?
Yeah, everything recorded, I believe.
Yes,
So
yes.
yeah, we can get the list of the attendant. Yeah.
Yes, and I think Dr. Pandey has a question. So he's asking, how are ITS-related operations handled during emergencies like flooding or hurricane events with GDOT?
Yeah, it's thanks for reminding us that that's one of the that's an interesting problem. So I rushed through a slide where we're talking about reversing lane reversals. So I was talking about the lane reversals on particular sections of the freeway where we are equipped to do that on a regular basis. But that's kind of what happens in a lot of situations where, means, if there is a hurricane happening in Florida and there or on the coast near Savannah, means there are hurricane corridors, designated corridors for evacuation, where we are equipped to shut down the ramps on one side and make use reversible lanes, or not reversible, reverse the direction of travel, so we have both directions going away from the coast towards the northwest inland, on the operations. And is the TMC interesting tidbit there, when the TMC has a 24/7 operation center, means that they are located right next to the FEMA building, and they also have place for operators to live there, sleep there for several days if required in case of those kind of emergencies happening where you need 24/7 operations. So I've done that a couple of times that I know about successfully, but thankfully we don't have to do that often. Does that answer your question? It's more manual than IT than automated, but the whole thing is about all the ATRs and all the detector and systems coming alive at that time to inform the decision-making team about the conditions on the roadways in real time.
Yeah, thanks. That was helpful. I appreciate it.
So I had like a following question with that. So do you also like have ITS system in the rural areas also, like how is that monitored?
So we have kind of a couple of batches of so the definition of ITS is kind of broad, right? So if you are talking about detection, real-time detection from infrastructure detectors such as the VDS systems, it's concentrated mostly in the Atlanta area and some in the Macon area. But the concept of ITS is much broader than that. Means the weighing motion data that you're getting from the weighing motion stations, means that information is useful. You have weather stations spread all across the state, which feed into the NOAA data as well. And so you have you get the travel time probe data, which is probably not as high resolution as your video detection system data, but still it provides you visibility into the operation state and across the state. So yes, means that there are different levels of ITS data, different forms of data that's available throughout the state.
Thank you. So we have another question. So LK asked, like, what inspired you to specialize in intelligent transportation and simulation?
I'm sorry, I didn't quite get that. Can you repeat?
So he's asking what inspired you to specialize in intelligent transportation and simulation?
That's an old story, I guess. Means so I started off in the simulation world, and then uh, moved into the world of data. So feeding data for calibration into simulation took me a step back into data, and then that kind of it's kind of backwards from where this presentation led. Like we went from descriptive to prescriptive. I kind of started my journey with prescriptive. Like, why can't we use all this data that we see to drive our operations? And 20 years later, I'm still figuring that out.
Yeah, and also we have a question from Dr. Khatar. So he's saying, have you thought about using AI or ML, and also any thoughts on using a digital twin?
Yeah, so let me see. Okay, I guess my slides are not going back anymore. Oh, there we go. So this digital twin, in this we did use AI, not AI. We used ML, the LSTM, the long short-term memory technique for purely for doing data imputation to fill up all the gaps in the data. This was one of those cases where the data was being transmitted over cellular connections. So the data was so patchy that it was hard to drive a real-time simulation with this kind of gaps. So we used an LSTM method to fill in the gaps for the input data there. The emergency vehicle preemption, we have used an ML technique for this. Transit signal priority, we are trying out a couple of different machine learning. I mean, the first one we tried was was an RNN, and then we moved on. It's the FOP right now, but yes, this was more of a traditional approach. Means we used the traditional methods instead of using any of the CNNs or RNNs, because we wanted to have a much better visibility on the cause effect relationship instead of using so-called black box approach. So most of these are using machine learning in some form or another. But yeah, thank you for that question. Is that's where we seem to be headed? Means with the recent advancements and the popularity of our focus on ML, means we are finding use cases for these and making these more robust every day.
So I think we have one more question from Javier. He's saying, could you explain what are the main difference between digital twin and a micro traffic simulation?
So a digital twin, you can think of it as a data-driven simulation. So you do a microscopic simulation, but then you take the field data to instead of having pre-calibrated data for your turn volumes or the input volumes at the edges, coming from a fixed period that you are simulating. You use real-time volume inputs from the field to drive the simulation. That way, you are not locked in to a particular scenario that you have calibrated your model for. You can see the real-time inputs coming into your system as as things change over time. You can also tie in, once that's the basic level, then you can tie in software in the loop simulation, where you can have software emulators of the signal controllers tied in, so that when you try out a strategy in your digital twin and it makes sense, it will be directly transferable to the field, because you are using the exact same controller logic that you have in the field in your simulation. So it's already tried and tested in the simulation environment when you translate it back into the field.
So we have one more question. It's how do you integrate machine learning models with existing transportation and simulation tools? How do you handle the variability and unpredictability of traffic conditions when designing machine learning based traffic models?
So yes, Ms. One of the so for example, in that in this emergency vehicle preemption model, we did not have an actual emergency vehicle preemption in the field. we were testing it out before where we are making the use case for emergency vehicle preemption. So how do we create a model for this when we don't have any real world data to work with? That's where the simulation came in. So we ran different scenarios with different traffic volumes, different corridors. We ran hundreds of runs to generate the traffic on which generate the data on which we could train the model. So that's one class of model. Is that there are different other classes of models where you don't have to have a training data set, but rather you train the models on the fly using the simulation in the loop. Right? So the simulation is being used as a tool to work with and train our machine learning algorithms, rather than using the machine learning algorithms as embedding it into the simulation. That's how my research group has been moving forward.
Sure, this is helpful. Yeah, thanks a lot. Thanks a lot, Dr. Guin, once again for your insightful presentation. I would like to now share my screen for the ones who would like to fill up their attendance form, while I'll also allow Basant for giving us the closing remarks.
So I really want to use this opportunity to thank Dr. Guin for sharing your knowledge and perspective. It has actually provided us with valuable insights. And then we truly appreciate your time and effort that you put into this. And then a big thank you to everyone that also joined us. We look forward to seeing you in our next coming events. Thank you so much.
Thank you. Bye.
Thanks a lot. Thank you.
Thank you.
Thank